Frans Vaas, and I'm staying at HSNL Village, which is a little bit further on here. So if afterwards you want to talk further with me, then you can find me there. This talk is also online. You can also find it to the program website. And it is I made it mobile friendly, so you can also look at it. It also has some extra notes with every slide, every part. So if you lost the track, then you can look up the notes, and in the notes there are also links to all kind of information. Okay, live-bootstrap, that is a Linux Foundation project that already exists for some time. And in this, and I've been reviewing it in the past 4 years, so I want to talk about it a little bit. Now, the content of this talk will be: what is live-bootstrap? Why do we need it? Then the question is how to review live-bootstrap. I will talk a little bit about the binary seeds, and then also about all the other sources. And then finally, I will look, maybe think a little bit about ways to improve live-bootstrap from a point of a reviewer. I think that some things can be done better to make it more reviewable. So, what has it all to do? It starts with the question, can we trust Linux? And with Linux, it's quite unique because it is open source, so we can look at all the sources. That's not like Windows or Mac OS, that is closed source, so you have no idea whether you really can trust Linux. But, and it's possible that you can build Linux yourself by taking the sources and then compile it. But then you need a compiler. A compiler is a program that takes a source in readable language and then transforms it to several steps into some form of binary that is in machine code, so that it can be executed by the operating system. But you have to start with a compiler, and the compiler is also in binary, so it's not in source form. And that leaves open the door to a so-called malicious compiler. A compiler that sometimes do something else than exactly translating the source to the binary, but inserts, for example, an SSH key, or inserts an alternative password, which would allow an outside attacker to go inside. Now, this is really not a new problem. Ken Thompson, one of the developers of Unix, he already recognized this problem in his Reflections on Trusting Trust speech that he held in 1984 for the Turing Award. Now, there are two approaches if you have something binary. The first thing is, maybe you can reverse engineer it. Now, with Linux we start with the GNU C compiler. That is an optimizing compiler, and it's quite big. So reverse engineering would be a lot of work, and reverse engineering is not very simple. And you have to go to all the machine codes, because somewhere in that machine code there could be something hidden. And it could be as simple as a system calling an all executable or something else. So, that's why the live-bootstrap project took another approach. It says, let's start with the tiniest possible pieces of machine code, and from there build all the tools that we need to finally build the tiny C compiler. And with the tiny C compiler, you can compile the GNU 4.04 version. And with that, you can compile the GNU 4.7.4 version, which is the last version that is written in C. All the other versions are written in C++, but luckily the 4.7.4 version can compile C++. So, and with that, you can compile the 10.40 version, and then finally you can build a quite recent version that is 13.10, and with that you can build the Linux kernel. So the question is, what is this tiny piece of machine code that we have to start with? For that you have to go to the bootstrappable seeds repository on GitHub, and the first thing you read in the README is never trust anything in here, because yeah, it could be malicious as well. So, but luckily they do provide the source code in machine code for this hex 0 program. The hex 0 program is a program that reads hexadecimal numbers and also it allows to insert some comments, and it makes it into binary. So each combination of two hexadecimal digits is translated into 1 byte. So if you have the hexseed program, then you could call it on the hex 0 underscore x86, and then it will produce an hex 0, and if everything is correct, it should be equal to the hex 0 seed, which you started with. These kind of programs are always target to the platform that you're working on, and I decided to look at the x86 platform, but of course you also have the 64 bits platform and the ARM and so on. So in the live-bootstrap there are several of these kind of programs for different targets. Now the question is, can we verify this hex 0 program? Now the first thing that I did is try to build something that does exactly the same. And I did this I did this by writing hex 0 program in Brainfuck. Brainfuck is a so-called esoteric programming language, and it only has 8 commands, namely these 8 characters. And so I wrote, with the help of some program, I wrote a Brainfuck program that exactly behaves the same as hex 0. And with this, I verified that indeed hex 0 is the binary form of what you read in hex 0 x86 hex 0. And the question, is this enough? It's really an interesting question. Is this enough to know that they are indeed the same? Or could there be some trick in this program that maybe if you put this input, it does exactly the same, but maybe for some other input, it does something else? So we also have to look at the code of hex 0 x86. Now, to verify that, you need to know something about the executable and linkable format, or the ELF format, in which all executables in Linux are made. And it started with Linux, but nowadays it is also used for many different platforms. Many embedded platforms, they put their executables in this format. So you have to know something about that format. Then, of course, you have to know something about 86 machine code instructions. So you have to look up some references. And last but least, you need to know something about Linux system calls. Now, I will show you now the source of this program. It starts with some comments that the hash character is a comment character, and also the semicolon is a comment character, which means that everything from the hash till the end of the line is considered comment. So here you see the first four hexadecimal numbers, and that is actually the magic number for ELF files. And then you have the header, saying something about the target, a lot of things about the machine, and so on. And then you have the program header that tells something about what is the machine code and where should it be put in the memory, and how should it be called to be executed. And then from here on, we have the machine code. You see here the hexadecimal number. Here you see some information about the instruction that it represents, and then some comment about what it should do. Now, of course, you have to verify. You have to take the book and look at all these instructions with their arguments and see if it indeed has this hex number. Now, there are some online tools where you can enter these, and then you can see if it's correct. Now, you see the program goes on. It has some loop, and it calls some other functions, and it has many jumps, and it's a little bit long. So you can look through this, and you can indeed see that it has nothing tricky in there. You also have to look at the interrupts here. It ends with a CD80. That is a call for the 80 hexadecimal interrupt call. And as you can see on the EAX register, it has a 1 value, and that stands for the exit operator. So you tell the program tells the operating system, I'm done. You may remove me from the memory and execute something else. Okay, so and that's all you can do about reviewing the binary sources and assure yourself that they're correct. But now what about all the other sources that are used in this live-bootstrap project? So the first question is, what are the sources? There's a description in the file parts.rts in one of the GitHub repositories that tell you all the steps that there are. And there you will also find a so-called kaem shell program, and that you can execute with a kaem shell, which is a very minimal shell, for which there's also a binary seed. And so there's several of these kaem scripts, and I decided to write a program to scan these scripts to see what they're doing and how they're calling each other, executing each other. And then at one point I also discovered that some kind of C compiler, or at least a primitive C compiler, was called. And so I also needed, and then you need to know which header files are included. So I also wrote a C preprocessor. And so I continued working through this, and then finally I noticed that it was also compiling the bash shell, and that it started executing programs in the bash shell. And then I thought, okay, I'm not going to write a parser for bash shells and an interpreter for that. I thought that's too much work. So I stopped it, and I published everything in a very large file that has all the steps in there and shows all the files that are read and the files that are produced, and also has all the source code with links to the original repositories where they can be found. I will not show that file now, but you can do it at home and read through it, and you can see all the sources that are into the live-bootstrap project. But I wanted to go a little bit deeper, and I was not sure whether my program was completely correct. Maybe it had some errors in there. So I thought myself, maybe I can write an emulator for a limited set of x86 instructions, and also a program that supports system calls. Actually, it simulates multiple processes, because in the program a shell will usually start other programs, and that programs could also start other programs. So I had in the program, in the emulator, I had to simulate multiple processes. For everything it writes to file, instead of storing that in memory, I decided to simply map those to the file system. So the emulator, it writes files and it reads files from the file system. It was not very easy, especially if you make some bug in your emulator and the instruction you implemented in the wrong way. You can get up in situations that are very hard to debug. But it was very insightful. And I also discovered that during the whole execution, that no other binary files were read or other sources that could be not be trustable. But it was too slow for compiling the GNU Mesh compiler, which is used to compile the tiny C compiler. So actually, I got less far than with the previous approach. So I thought, yeah, that was a little bit pity. And I stopped with this then. And then at some point I discovered strace, which is a program that you can run on Linux to trace system calls. So I wrote a Scroll script that executes all the steps of live-bootstrap, and I run it within a root, alternative root environment that you can use with chroot. And that produced a very long log file, and I wrote a program to parse this log file and put everything in JSON file, and from that one I generated a T diagram. Now, what is a T diagram? Of a tombstone diagram. A small one looks like this, and you see here 3 T-shaped outlines, and in the outlines you see on the left side you see the source language, and on the right side you see the target language, and at the bottom you see the implementation language. So here we have a C program that takes hex 0 input and produces some binary output. Here we have what is a C compiler. It is an executable, an ELF executable, and it reads a C program and it produces an ELF executable. And if you take this as input, then it's transformed into an ELF program that reads hex 0 and produces binary output, which could be an ELF file itself. So this explains how you can make how a T diagram works. Now, the T diagram that I have produced, it looks like this. And if you zoom in a little bit, we see here, here below, we see in red, everything in red is signaling the seed programs that we're using. And the green lines are used to show which programs are executed by which program. So this program, hex, the second one, is executed by the first program that is executed. And here we see the hex, the seed program that is executed, and it takes the hex 0 x86 program, which is a program that is written in hex 0 and reads hex 0 and produces it into an ELF, and that will produce hex 0, which is equal to the hex 0 seed, and that is a program that reads hex 0 and is an executable in ELF and reads hex 0 and produces an hex. Now, and with this, you can go on. Oh, sorry. I zoom a little bit, and you see some other hex inputs and some other in something in the M language, and then in C2 and C1. Here, C1, C2. And it continues a little bit, and it continues a little bit more, and it continues a little bit more, and a little bit more, and a little bit more. And then here we arrive at the MES GNU compiler, and it goes a little bit more further, and a little bit further. And then here at the end, we zoom in again. We see that after 732 processes have been called, we have something that is called TCC boot 0. And that is the first compiled version of the TinyC compiler without support for doubles. And with this, you can finally start to compile the TinyC compiler sources into the really TinyC compiler that you can use to compile all the GNU compilers. And in this diagram, you find that C1 and C2 are two subsets of C languages. Now, why is this GNU MES compiler so slow? Now, the reason is that it's a C compiler that is written in Scheme, and Scheme is a variant of dialect of Lisp. It comes from Lisp originally, and it consists of a Scheme interpreter in a subset language of C, of the C language. And actually, if you look at the C compiler, it has an LLR parser, and that is also interpreted. So the program itself it makes also use of an interpreter. So it is a double interpreter. So that's one of the reasons why it is rather slow. But before you have to get the GNU sources, you need to unpack it from a zip file. And so you also need a C language that is good enough to compile two utilities. So I feel a little bit that the GNU MES compiler is a little bit on the level of the TinyC compiler, and also it is preceded by a compiler which is already quite complete. So I feel it's a little bit the odd one out, and I'm not the only one. I've also read other people making comments like, why not use Forth? It's a stack-based language, and maybe it's much easier to write a compiler in this language. So that made me think about a GNU MES replacement. And so this is one of my observations, that GNU 0 is a short but rather cryptic program, and it has only some descriptive comments about what it is. I don't know what equivalent of C code it represents. And then there's some more sources in assembly, more than 6,000 lines. And you also have to go to all of those, also commented in the same way. And And so, yeah, these source codes implement two subset of C compilers. It also includes a C preprocessor, which is not a trivial program. And the last C compiler and the C processor, they are good enough to build the untar and the ungnu-zip program. And then still, if you want to check the compiler, you have to read through a lot of scheme. And I'm not very familiar, although I have experience with Lisp, I'm not very familiar with scheme. And it's a lot of sources in many files, and I haven't started reading it. So actually, I do not know everything about whether we can trust it. So my idea was an alternative approach that is based on a readable intermediate language, and that also has more loops. And the idea that I have is that then the T diagram would look something like this, which is a little bit smaller, and then at the end I hope that I have a C compiler with which I could compile those utilities, and also the tiny C compiler. And you also, in here, you see a lot of blue lines, and that means that the source that is produced here is also used there as input. So that means that things that you take as input already in a form that is produced by another step. And to a little bit show you my idea of the intermediate language, let's start with a simple C assignment statement. And the intermediate language that I approach, that looks like this, which is actually just the steps. It's a reverse Polish notation. So you this Y says like, okay, put the address of the Y variable on the stack, then put the variable of the address of X on the stack, and then use the query operation to get the value from that location on the stack. Then put 1 on the stack, add the two top values, and then perform the assignment, which uses this address and puts the value in that address. And then finally the same semicolon, which is equivalent to a pop operation, because in C an assignment always returns the value that it assigned, so that you can chain the assignment operators. Now in the M1 assembly language that is also found in the live-bootstrap project, this would look like this. So you have the, and you see here, in the comments, you see exactly the line that we already had. And then you see also the mnemonics of the instructions that need to be executed. And then if you put this to the M1 assembler, then it could output something like this, which gives you the hexadecimal numbers of the instructions with the exploded arguments of their values. And you can very easily verify that, yeah, I see here a push operation, and that matches with this 50, and here I return it again. So you can quite easily verify that this is really a one-to-one map. And if you then put it into if you put this with some other sources together, then you can make an executable out of this. Now, what should be the properties of this intermediate stack-based language? It is stack-based, and the idea is that it is close to C, that it has a simple mechanism to declare variables, that it also supports the block structure with local variables, that it has functions, that it has some support for structs, and that it is simple to compile to M1 assembly. Now for this I used two stacks. One stack is the stack that you already saw. That's the stack that holds the variables, and the other stack holds all the local variables. So whenever you enter a block or whenever you call a function, then the stack will be incremented and will contain all the memory locations that are needed for those values. And in the language I only use C keywords for practical purposes. Otherwise, for practical purposes. And now already started working on a C compiler that compiles to this low-level intermediate language. It has a built-in preprocessor. The nice thing about tiny C compiler sources is that you can compile it as a single file that includes all the other files, and so you don't need to have something like generate object files and then have a linker. So if you have, made it possible to put the preprocessor in the program in the C compiler. It's a single pass recursive descent parser, which is simply written with recursive calls with functions, and it does on-the-fly code generation to the stack intermediate language, and it only uses an abstract in AST, an abstract syntax tree for the expressions, because you have to reorder something, and sometimes you also have to figure out something about the types, because for signed operations you have different operations than for non-signed operations and things like this, and you have to know the size of the values that you're working with. Now, this compiler is already self-hosting, so I can compile it itself with it, together with some of the tools from live-bootstrap, the M1 compa, the M1 assembler, and the hex0 program. And now I'm working on compiling the TCC sources. So that brings me to the end of my talk. Are there any questions?
So, as far as I know, the mass project also provides a libc, which is used up until glibc muscle is compiled in the bootstrap. Are you still using that, or are you planning to replace that as well?
So, sorry, say it again.
The MES project also has a libc. Are you still using that, or are you working on replacing that as well?
Yeah, currently I'm writing my own C library, but maybe I could reuse it. Maybe I haven't thought about that. In the beginning, in my own compiler only needs a few operations, but I've already noticed that in the tiny C compiler there are far more functions. So maybe I should use it and instead of writing my own library. That's a good idea. Thank you for the suggestion.
Quick question. So thank you for your talk. It was nice. Can you? Quick question. Can you tell me whether the C compiler that you're building is that also can that also be built from the intermediate language that you?
Maybe I should go back to the T diagram and show you a little bit what's the idea is that. Now I have to search a little bit. Actually, the compiler is up here, and here are the sources of this. Which it's also, of course, it's a subset of C, and so this is the TCC_C program, and I executed with a compiled version of itself, and it produces a TCC_SL, which is in the stack language. And that can be taken as input by that can be by the stack, the compiler that I wrote for the stack language, and that produces a TCM file that you can then produce. Finally, will result in an hex file, and then this hex file you can see that it goes to the next step in here. And it will, I don't know where it goes exactly, but you can see that at the end I will loop it back, and then I will finally arrive at the binary, and then I can compile it with itself. But because I made this change, you can always, it loops back, and the project includes a make file that repeats some of these steps and actually runs it with itself and see that it produces exactly the same input when it executed on itself and produces exactly the same intermediate language file. And the stack compiler also have the intermediate language for, and so that's how it is put together. So if you go to the notes, then I have also all the links to the GitHub repositories and it shows many notes here. So you can also look maybe I have the notes in here. No, I have no links, but it has also links to many of the blog posts in which I write about the development, and in there you can read the whole story in more detail, and also read about all the things that I stumbled against and all the detours that I took to finally arrive at this.
Thank you.
So you did some of the part of live-bootstrap here.
Yeah.
Do you have a feeling for how many people would be necessary to check each and every code or reproduce each and every code to finish at the last step? I think that's the Linux kernel.
Yeah, it's one of the reasons that I hope that with my approach that review will be a little bit easier, because you don't have to know scheme, you don't have so many sources. It's all in one C file finally, of a number of C files, and also you can see it's. I hope I haven't finished that, but I also hope that it will put all the comments in there so that you can really track it, and also track it back to the source lines with part of kaem for that. And for that, I hope it will be better or easily to verify than what is currently there. So it's not only that that I can do better, but also I think this is a way that I hope it's easier to review than what there is there now. Although I really appreciate it, and I think it's a very great achievement that they made it all together, because it's really hard to do it like this. So, but there's also always room for improvement, I think. So, yeah.
With questions? 2 times? Okay. No? Okay, then I actually need to thank Franz for his really inspiring talk. Give him a really big applause. Thank you very much.
Thank you.